Now let's discuss the membrane elements with incompatible modes. Now we know that when we generate an element by using the bilinear shape function, it locks, right? Under constant moment we see very stiff behavior, and we said that the reason of this stiff behavior is due to having a linear displacement interpolation within the element. So let's put that as a note and then continue. We said that quadrilateral bilinear membrane elements exhibit shear locking, or we also call it membrane locking. Excessively stiff behavior under bending. Now, since the reason of this excessive stiff behavior is the linear displacement interpolation, and in order to overcome this problem, we can introduce higher order terms. So in order to overcome this problem, one option is to add a higher order interpolation, or let's say higher order terms to displacement interpolation functions. So that could be a solution, but we have a problem. Now I want to do it for a 4-node element, 4-node quadrilateral element. And remember that at every node we have 2 degrees of freedom. Let's draw that. V1, U2, V2, U3, V3, V4. And by using these 4 horizontal displacement values, I can only define a bilinear shape function. So if I want to define higher order terms, I should have more variables, right, in the x direction, for example. But as an alternative, if you think about the Rayleigh-Ritz approach or the beam element with the general displacement field, I don't have to use the nodal displacements as a variable in my shape functions, right? I can use any polynomial interpolation within the element, provided that I satisfy the, for this element, C0 continuity requirement and the essential boundary conditions at the nodes. So these are the requirements, but within the element I can actually define any shape function that I want. So keeping that in mind, what I'm going to do is, now we have our typical shape functions, bilinear shape functions. So these are, again, I'm using the bilinear shape functions. And I am adding 2 general terms with higher order polynomials. Oops, let's call it A2. And the vertical displacement interpolation will be Again, I will be using the bilinear shape function plus the same type of higher order terms. So as you see, I define my higher order terms as follows. So when I'm at this node, these ones have 0 values. So at every node, these higher order terms will diminish. Okay, so I end up with only these bilinear shape functions, and this function satisfy the essential boundary conditions. So as well as it is continuous, one-time differentiable and continuous. The problem is these A values doesn't have any physical meaning. So they are actually the generalized displacements. So let's take a look at what will happen if we calculate the strain displacement relationship with this new shape functions. So I'll again write this relationship. So I have to figure out what the B matrix is so that I can calculate the element stiffness matrix. Now I will partition the B matrix into two. B for the nodal displacements and B for the generalized displacements. And this time the U vector will become U1 V1, U4 V4, and here I have A1, A2, A3 and A4. Now how do we calculate this BA matrix? Now BU, this part is exactly the same as the bilinear membrane element. So we have this additional terms for the generalized displacements. Now if you remember our Jacobian matrix interpolation, if I want to take the derivative of function with respect to x, and if this function is defined in the natural coordinate system, I can calculate del f over del x as follows. Jacobian 1 inverse multiplied by del f over del x plus Jacobian 2 minus 1 del f over del nu, right? And likewise del f over del y will be equal to Jacobian 1 inverse del f over del psi. Sorry, I have to make this one should be equal to psi plus Jacobian 2 inverse del f over del nu, and my u is equal to, let's write it one more time, del ni ui plus 1 minus psi squared a1 plus 1 minus nu squared a2, and I want to calculate del u over del x. This is my axial strain in the x direction, and let's focus on this new part of the equation because we already calculated del u over del x for this part in the bilinear membrane element. So I'm using this approach, and this part will be equal to J11 inverse del f over del psi, so minus 2 psi multiplied by a1 plus J12 inverse del f over del nu will give me minus 2 new A2. And del V over del Y again, I will take the derivative, which is, or let's write this, calculate del U over del Y, sorry for that. That will be equal to J21 inverse minus 2 psi A1 plus J22 inverse minus 2 nu A2. We can do the same thing for the V, del V over del X and del V over del Y. And at the end of the day, my BA matrix will be equal to J11 inverse multiplied by minus 2 psi, J12 inverse multiplied by minus 2 nu, 0 and 0. Here I have 0 and 0, J21 inverse 2 psi, we should have minus, J22 inverse minus 2 nu, and the third row will be J21 inverse minus 2 psi, J22 inverse minus 2 nu, J11 inverse minus 2 psi, and J12 inverse minus 2 nu. And this would be the B matrix, so we add it to the end of the B matrix. Now after calculating the B matrix, we can calculate the stiffness matrix K with our typical equation, which is B transpose times E times B times dA. Now in that case, B will be a 12 by 3 matrix, E will be 3 by 3, and this new B will be 3 by 12. And at the end of the day, when you calculate the K matrix, K will be a 12 by 12 matrix. So what we need to do is, so before assembling, K into structural stiffness matrix, it is a common practice to condense out the generalized displacement terms. So what we do is, I have this element, I have A1, A2, A3 and A4 in this element. I calculate the stiffness matrix for the nodal displacement and as well as these generalized displacements, and then I condense out these terms A1, A2s, and I end up with an 8 by 8 matrix written in terms of these nodal displacements only. That's a common practice for this type of elements. So there is no rule or a relationship. Let's write it, relationship for the generalized displacement terms of different elements. So let's again work on this two-element example. And let's say that this is the undeformed state. And we see some deformation. Now, if this element is a bilinear element, okay, we calculate the locations of the nodes. Let's plot these nodes. So let's say that these are the new locations of these nodes, and if you plot full displacement field of this element with the bilinear interpolation, this is what we see. So the displacements of any point within the element will be calculated by using the nodal displacements. So this is with bilinear shape functions. But now I will draw the same figure with incompatible modes. Now remember that the displacement of this element is now written in terms of the first element is now written in terms of nodal displacement and as well as the generalized displacement terms. So let's say that due to that I can have curves now. This could be the deformed shape of the first member. But since the generalized displacement terms of the first element and the second element are not linked, I may see some overlaps or gaps between the elements due to having different unlinked displacement field definitions. Okay, so here what we observe is in these elements overlaps or in displacement interpolation. That's why this type of elements are called incompatible elements. Or defining the generalized displacement in the displacement field is called an incompatible mode, right? So again, let's repeat what we meant. So due to having these AI terms, the generalized displacement terms in our displacement interpolation, and since we don't have any relationship that link these AI terms between different elements, as the final step when you calculate the nodal displacement and when you plot the element deformation of every element, you see that the edge displacements of the elements are not compatible. They are not the same because of these AI terms. That's why they are called incompatible elements. But the advantage of this element, which we will also see in the implementation example, we now introduce a higher order terms to our displacement field, and we expect that these higher order terms will solve the shear locking problem. Now let's take a look at the implementation of the quadrilateral membrane element with incompatible modes. Now here I'm defining two different shape functions. One of them is the bilinear shape functions. This is it, and these are the derivatives of it. And I have introduced new shape functions, the higher order terms, 1 minus psi and 1 minus nu squared, and these are the derivatives of it. Now, of course, the Jacobian matrix is calculated by using the bilinear shape function. Why? Because our coordinate interpolation hasn't changed. So I'm interpolating the coordinates as follows. So that's why I have the same Jacobian here. Now let's continue. Of course, the only difference here is between these two elements is the strain displacement matrix. So this first part is exactly the same with the bilinear element. I'm just filling the first 12 columns of the B matrix as I did in the bilinear element. So now the only difference is the additional part. So this is not 12, between the first 8 columns. So between 8 and 12, I am filling the BA matrix. So B matrix is filled with the BA matrix. So Jacobian 1, 2 times dn, or the derivative of the first derivative, which is minus 2 psi, Jacobian 1, 2 multiplied by the second derivative, which is minus 2 to nu, right? So second row, I'm filling 10 and 11, Jacobian 2, 1 times minus 2 psi, Jacobian 2, 2 times minus 2 nu. And at the end of the day, I will have a 12 by 12 matrix. Now I have the condensation routine here. Now this is a little bit from what I described in the static condensation topic. There I was using the matrix multiplication, but here this is actually an algorithm for an unfinished factorization. So I'm just factoring up to the first number of elements, and this will give me the condensed stiffness matrix. We have the same constitutive relationship. So I'm forming the element stiffness matrix. Now it condenses out the bottom 4 terms in the stiffness matrix, and at the end of the day it will give me 12 by 12 stiffness. This is again the same algorithm for the force. Calculating the equation numbers is here. I'm assembling the global stiffness matrix and then the solution. Of course, let's now take a look at the same example problem. If you remember the bilinear example, we were like getting 20 times smaller displacement because it's a very stiff, it locks and it gives us very stiff behavior. Now the actual tip displacement, let's write it here, T exact, is equal to 0.00237 no shear deformation. So if we have shear deformation, this displacement becomes equal to 0.0024. Okay, this is the width shear deformation. So I'm solving this cantilever by using a single element, and when I look at the displacement, they are equal to 0.0018. They are not the same, but they are very close. Remember our 5-element solution with the bilinear elements? The 5-element solution will give me almost half of the displacement, but with this introduction of this higher order terms in the shape function, I was able to get 0.0018 with a single element. So now we significantly improve the behavior of this membrane element under bending action. What will happen if I use more elements? So this is the case with 5 elements, and the result is 0.00238 as the tip displacement. So it's somewhere in between. So we can say that, you know, we catch the bending behavior very, very nicely. Now the shear deformation, we are not there yet, but maybe if you just divide this element from the middle, you'll get a better approximation and better displacement interpolation. Sorry, displacement calculation.